Hello students, welcome back to Algebra 2. We are in section 6.3, which is an introduction to logarithms. Got a lot to cover, so I'm going to go quick. So, first of all, I don't like ever teaching a topic without giving it some context. This lesson doesn't really have any context until we get into the application. So first we need to learn what logarithms are, and then we need to learn some advanced techniques, and then after that we get some context. So I'm going to jump ahead a little bit and just give you an idea of where we're going with this. So for example, we started talking about a problem like this. You have $10,000 that you invest into an account that yields 3%. Oh, I spelled yields incorrectly. Yields 3% interest annually. So if we wanted to write an equation for that, we would say, okay, y is equal to 10,000 times 1.03 to the x power. This is what we've done in previous lessons. Now, if we wanted to ask the question, how much money will you have after 10 years? We could just replace the x with a 10, and then that would be fine. However, if I wanted to ask the question, when will your investment be worth $50,000? Well, now I get this. I would change the y to 50,000, and that would equal 10,000 times 1.03x. If I divide by 10,000 on both sides, I get 5 equals 1.03x. And now we're to the point where I need to get that x out of the exponent. That way I can solve for it. Now, methods that we've used in the past, if that x had been a 3, for example, 1.03 to the third power, I could take the third root. So we might think about trying to the xth root, but then I would get 1.03 equals the xth root of 5. And at that point, I don't know what to do with that either. So this is where logarithms come in. Logarithms are going to give us a way to get the x out of the exponent to a point where we can solve it. So let's go ahead and talk about the definition of a logarithm. So I'm going to start off with concrete numbers, and then I'm going to move into abstract variables in order to define this. Okay, so let's take a very simple exponential problem here. So first I'm going to have exponential form. An exponential form is going to look like this. 2 to the third power is equal to 8. Now, taking that, I'm going to change it into logarithmic function. I'm sorry, logarithmic form. That would be log base 2 8 is equal to 3. Okay, so each of these questions is asking two different things. So in exponential form, it is saying 2 to the third power is what? This one would say 2 to what power is 8? So, abstracting that into variables, exponential form would be a to the b power is equal to c, while logarithmic form would go log base a c is equal to b. Now, a quick way that students are taught to remember this is with the hook rule. And the way we use the hook rule, I'm going to move over here, is if I say log AC is equal to B, is that we circle the A and we go A to the B power is equal to C. So A, go across to B, A to the B power is equal to C. That's what a logarithm is. Okay, so changing from logarithmic form to exponential form, this is pretty straightforward. So if I say we get a problem that's like log 232 is equal to 5, and I ask you to change it into exponential form, well, you just use that little hook rule. Just like that, and that would change into 2 to the 5th power is equal to 32. Oops, not 3 to the 2nd, 32. Okay, now what if we ask you to go backwards? If we say, well, 3 to the negative 2nd power is 1/9. Then we would go log base 3 1/9 equals -2. Easy enough. Okay, evaluating logarithms, we would say something like this. Log base 3 27. So the question that we're asking there is 3 to the what power is 27? So you can use your calculator and you can test a couple things until you realize, oh, 3 to the 3rd power is 27, so the answer would be 3. What about log 5 1 over 125? Now this one is asking 5 to the what power is 1 over 125. Hopefully you remember your properties of exponents and you remember that the exponents that make things turn into fractions are negative exponents. So 5 to the 3rd power is 125. So therefore 5 to the negative 3rd power is negative. I'm sorry. That was a mistake. 5 to the negative 3rd power is 1 over 125. So the answer here would be -3. Log pi 1 is equal to, so what this one is asking is pi to the what power is equal to 1. Now the reason I chose pi for that one is because I said 1, and we should remember that anything to the 0 power is 1. So pi to the 0 power is 1. So log pi 1 is 0. One weird one that I feel I should point out is, what if I said log 3 0? So it would say 3 to the what power is 0. And hopefully you see this is not possible. 3 to any power will never turn into 0. So this one would be undefined. Okay, so we've got some special logarithms. One of the things that you should notice is that anytime we have something like this, log 3, anytime these two numbers match, the answer is always going to be 1, regardless of what it is. So if I had log pi, the answer is 1. It's a little fact that you're going to use quite a bit. Now, if I ever have something that looks like this, log 7. Now, if you notice, the weird thing about that one is that there's no little number at the bottom. There's no base on this one. If ever you have log with no base, what that means is there is an invisible 10 right here. So this is called the common log. Anytime we have something that just says log, that's the common log, that is implied that there is a 10 there. Another one that is very common that'll pop up is LN. LN stands for log natural, or in English, natural log. This was invented in France, that's why it's LN and not NL. So if I had LN7, natural log of 7, what that is saying is that it's actually log but instead of a 10 there, it's going to be an e. It's going to use the natural base e that we learned about earlier. Okay, now the thing that's special about these two, common log and natural log, is that these can be done by your calculator. So if you need to do a problem in your homework and it says what is log 7, you just type in log 7 into your calculator. If it's not log 7, if it's not common log, and if it's not a natural log, then we have a trick coming up in a future lesson that'll help us with that. Okay, inverse properties. Now this one's kind of interesting. If I have a log with a base here, let's say 7 again, and then 7 to the x, something weird happens here. So one thing I want to point out real quick, and this is going to be a small logical jump for us. If I have log 5, 3 is equal to log 5x, what does x equal? Hopefully you can say that x is 3, because you see both sides of this equation are identical except for the x and the 3, which are in the same spot. So if log 5, 3 is equal to log 5x, therefore x must equal 3 because they're in the same spot. Same thing with exponents. If I have 5 to the third equals 5 to the x, in this case, x has to be 3 because both sides of the equation are the exact same, except this one's got an x and this one has a 3. Okay, going back to this. In this inverse property, what happens here? Well, I want to say log 7, 7x equals something. I don't know what it is. But now that I have it set up like this, what I can do is use that hook rule that we talked about earlier in order to rewrite this as an exponential. And what that's going to say is that 7 to the something is equals to 7 to the x. So 7 to the something is equal to 7 to the x. And based on the property that we just discussed, that means that that something has to equal x. So that means that log 7 to the x power just equals x. Now that we've shown that property, if I ever want to use that, I can say if I have log of 13 to the pi, I can just say, oh, log 13, these are going to cancel each other out, and the answer is just pi. In a similar fashion, what if I have 7 to the log 7 x power? Okay, in the same way, I'm going to say I don't know what that equals, but I can do this going backwards. So I have 7 to the log 7x equals question mark. So rewriting that as a logarithm, I can say log base 7 of something is equal to log base 7x. So therefore, the something has to be x. Again, what I can do here, now that I've shown that, is I can just cross these off and say the answer is x. Okay, now one more. Writing an inverse function. We've done inverse functions in the past. So real quick, I'm going to go over how to do an inverse function with a linear function. So for example, if I have the function y equals 2x plus 1. This is my regular function. If I want to write an inverse function, the way that I do that is I switch the x and the y, and then I solve for y. So I'd subtract 1, x minus 1 equals 2y, and then I'd divide by 2. So I'd get y equals x minus 1 over 2. That's how I would do it with a linear function. Now, how do I do it with an exponential function? So if I start off with an exponential function like y equals 3 times 2 to the x, I'm going to go ahead and switch the locations of the x and the y. So that means it's going to be x is equal to 3 times 2 to the y. In order to get in order to get the y by itself, first thing I'm going to do is divide by 3. So I have x over 3 equals 2 to the y. And now I'm going to rewrite this using a logarithm. So that means it would be log base 2 x over 3 equals y. And now I've got y by itself, so that's my inverse function. Let's do that one more time, but this time going backwards. What if I had the function y equals 4 log 7x? If I wanted to write an inverse function for this, again, I'm going to switch x and y. So I've got x is equal to 4 log 7y. To get this by itself, I would divide by 4 on both sides. So I would get x over 4 is equal to log 7y. And now I would change it from a logarithmic function into an exponential function. So 7 to the x over 4 equals y. 7 to the x over 4 is equal to y. And that is my inverse function.